In this slide, we are talking about stability. Specifically, we are interested in BIBO stability. BIBO, BI stands for bounded input. BO stands for bounded output. We are saying that if our input signal is bounded, that means it doesn't grow to infinity, our output is bounded. How do we check whether we have a BIBO system or not? In this slide, we'll show that a BIBO system is verified by checking its impulse response. If the impulse response is absolutely summable, then it will show that our system is BIBO. Let us see why is this so. We begin with the convolution equation, and this is the convolution equation, and all we are given is that x of n is bounded. That means the magnitude of x of n is always less than or equal to some big value k. Okay? And we want to see whether y of n is also bounded. That means it will reach some value, but it will never exceed the value ky. The proof goes like this. We take the absolute on both sides. So on the left, we have the absolute of y, and on the right hand side, we have the absolute of this convolution equation. Now, remember that this term can be positive or negative. If we take each of these terms as absolute value, therefore we are always adding up, implying that this summation is greater or equal to this previous expression over here. Remember then, we are told that the input is bounded. So we substitute kx to represent the largest value that we can ever observe in the sequence x. So when we can substitute this as kx, then we realize that the only thing affecting the output is absolute value of h of m. So we move the kx outside, and then we are now left with the output being only affected by the impulse response, or I should say whether the impulse response is absolutely summable. Once the impulse response is absolutely summable, this value times the maximum value of k will bound my output. And hence, to prove whether the system is BIBO or not, all we need to do is to check this condition. In the next slide, I will show you how to study this from the pole and zero diagram. Here, if we have h of n representing the impulse response, and we get h of z, the transfer function, then we only need to observe the pole position. Here, I show you how different pole position will generate different h of n. When the poles are inside the unit circle, the h of n will decay. If the pole is outside the unit circle, even by a little bit, the h of n will grow. And if the pole is on the unit circle, then the h of n will basically alternate and will not decay or grow. Of course, if you have a pole, second order pole here on the unit circle, it will grow bigger. And now we'll show you how different pole positions will generate different h of n. Now, I think these examples on the right, again, we have a pole inside the unit circle. Here is a exponentially decaying signal. What is different from here to here is that this is along the positive real line, and here is along the negative real line. And hence, this is actually having a omega of pi. That means at every sample, he will generate a pi phase shift. That's why this guy is alternating at every sample. While here, the angle is 0. He's not alternating. He's just decaying because he is not on the unit circle. Once he's outside the unit circle, he's growing. And when he's on the unit circle, he's not decaying. So you have to learn how to interpret how the pole position would generate different diagrams. And once you have understood this, you realize that for Bibo system, for ZTransform, all we need to know is whether any of the pole, all of the pole are within the unit circle. Only when that happens, then the system is Bibo. Now you might be wondering about all these complex conjugate pole. You realize that when we have complex conjugate poles, a cosine or a sine will form. Okay, and depending on whether the pole is inside the unit circle or not, in this case inside, then he will decay. When he's on, he will oscillate and he will not decay or grow. Okay, and when he's outside, he will grow. The complex exponential will be rotating and it will grow. So with that, you will see that one of the reasons why we plot pole and zero diagram is to very quickly determine if the system is Bibo or not. So why is this true? It's because the region of convergence actually tells us if the sequence is summable or not, absolutely summable or not. Since if the region of convergence is on the unit circle, Z is 1. Therefore, the region of convergence, if includes the unit circle, shows that this sequence will converge. And the pole always determine where is the region of convergence. So for example, if we have a pole here, we should be drawing this diagram here and say that if this is a causal sequence, anything outside this radius is the region of convergence. And once it includes the unit circle, what it means is that Z is equals to 1. Therefore, H of n is absolutely summable. That is the key idea why we are interested in the unit circle being in the region of convergence or not, because this is equivalent to exactly this equation here. So with that, the final take-home message is this: a causal LTI system is Bibo stable if all the poles are inside the unit circle. Thank you.